Hello, everyone. Welcome to this session of AI Infrastructure Week. I'm Sulagna Saha, and for this session, I'd like to welcome Steve Douglas, Head of Market Strategy at Spirent, now part of Keysight, who will lead this presentation, Stress Testing Networks for AI Workloads. Welcome, Steve. Please take it away. I think there's a problem with the audio. Steve, I think, I don't know, for some reason the audio is not on. It's still, I still can't hear you.
Lanya, can you hear me now?
Yes, we can
I
hear you.
apologize, everyone. I think we had a little bit of a technical glitch at my end. I'll jump straight in. If you didn't hear me, I just said it's a pleasure to join you. We're going to be giving you a recommendation on the what, why, and how to test your AI infrastructures. So look, jumping straight in, I just want to talk a little bit at the start here, a bit about setting the scene in terms of what needs to be tested and why it needs to be tested. And over the last 18 months, the AI infrastructure map has evolved. You know, if you take on the top left there the hyperscaler data centers, which have been the initial foundation of today's AI infrastructure build-outs. Traditionally, you know, they've been designed for high performance compute architectures, and you're now seeing them evolving from that traditional three-tier fat tree topologies to a more streamlined and efficient dedicated back-end architecture using spine leaf two-tier designs. And this is due to the radically different traffic being generated by the AI workloads. So in those classical environments, traffic was largely predictable with structured patterns. However, AI training and inference introduces highly dynamic and non-deterministic communication patterns, which lead to inefficient resource utilization, training integrity issues in many cases, and slow response times. So a new architecture was simply required to minimize the number of hops, to offer horizontal scalability and ensure a consistent high level of throughput and lossless communications. Now, on the national level, on the top right, what you're seeing is general purpose clouds are increasingly being augmented by neo clouds and sovereign AI factories to address the growing need of data sovereignty and AI specialization. In regards to neo clouds, you know, you're introducing architectures tailored specifically for high performance AI and data intensive workloads. Meanwhile, sovereign AI factories serve as national scale platforms that are combining compute, data, and model development capabilities under local jurisdictions. And then at the bottom, you have your telecom networks. And similarly, AI infrastructure here is starting to be distributed right across the radio, the edge, and the central data centers. The central data centers are evolving to host GPU as a service to efficiently deliver on-demand AI acceleration towards enterprises and sovereign AI ecosystems. While at the edges, many are being enhanced to become GPU-enabled micro data centers to host AI inference, split inferencing, and bringing data pre-processing closer to the users and the devices. And meanwhile, even in our radio environments now, AI-driven functions are enabling adaptive beamforming, localized model execution, and we're setting the scene for a future AI-native radio architecture. So lots of moving parts here on the infrastructure side. Now, one thing is clear from the sort of the early implementations of the AI architectures is that AI traffic is fundamentally different from conventional network traffic. And this is a big reason why testing is so critical. That's because it's dominated by massive bursty data exchanges between compute nodes, rather than the simple client server or transactional flows we're used to. So the AI workloads generate highly parallel, bidirectional, and bandwidth intensive flows with very, very strict latency and synchronization requirements. And if you just look at the AI training traffic there on the left-hand side, it's highly east-west intensive because it involves large, continuous server-to-server communications during distributed model training. It demands incredibly high throughputs to transfer the massive data sets and the gradients efficiently. And it's absolutely packet loss intolerant, as even minor losses can disrupt synchronization and actually degrade the accuracy of the whole training process. Now, the traffic, traffic is latency and also congestion sensitive, requiring deterministic low latency to maintain the training performance. And on top of that, it must also support complex collective communication library traffic patterns. Now, they're used to coordinate the data exchanges between thousands of interconnected accelerators. While in contrast, on the right-hand side, you have inference traffic, which is going to require high connection rates and concurrency because you've got huge volumes of devices and applications which are simultaneously querying the AI models in real time. So that means the transaction volumes and sizes vary widely depending on the complexity of each request, leading to bursty and unpredictable intensity spikes. And these workloads also experience variable latency due to the changing compute and network paths that they have to go through. And they're also, unlike traditional downlink-heavy services we're used to today, inference often generates higher uplink traffic as multimodal data is sent for processing. So these behavioral requirements mean networks for AI must be designed and tested to deliver deterministic performance, scalability, and dynamic workload orchestration far beyond the conventional sort of IP-based traffic we've been used to deal with today. So, if I want to take that just one step further and just look specifically at our telco networks, what you're seeing today is that AI inference traffic, although it's in its infancy, and it's less about growing data volumes, what you're seeing, it's about managing dynamic and unpredictable behavior patterns created by real-time AI applications. Now, I'm just highlighting some of the workloads above, but what you can see is that they're generating bursty high connections and latency sensitive traffic that challenges a lot of our traditional design assumptions of networking. And this means you're requiring in the future adaptive architectures that are going to have to be optimized for these AI-driven service interactions rather than just purely raw throughput. And as AI traffic does grow, and even if that is somewhat offset, as some of the industry are predicting, the strain on our existing architectures from this compounding effect could become detrimental, increasing latency, causing buffers to overflow, reducing throughput, all of that which could severely degrade service quality, especially if you're going to offer inferencing as a service at the edge or GPU as a service. So I think it's fair to say connectivity is becoming the linchpin for AI scaling. And what we're seeing is an array of technologies being introduced into the networking architectures. In our data centers, technologies such as high-speed Ethernet, RDMA or RoCE v2, the new Ultra Ethernet transport protocols are all vital for scaling because they deliver the ultra low latency and the massive bandwidth needed for distributed GPU training and inference. And these technologies, they enable efficient communications, minimize congestion and packet loss, and are really offering that high performance fabric required to interconnect thousands of accelerators across AI clusters. Then in our telecom and enterprise wireline networks, you're seeing technologies such as high-speed Ethernet, flexible Ethernet for hard slices, MPLS segment routing for soft slices, all essential for monetizing and managing traffic flows. They're there to enable the deterministic performance, the traffic isolation, ensuring that the AI workloads receive the guaranteed bandwidths and latency. And combining those capabilities is allowing operators to deliver those differentiated based AI connectivity services. And then in the wireless and our edge networks at the bottom there, you're seeing technologies such as our 5G standalone and advanced networks, leveraging things like network slicing, low latency, low loss throughput, alongside now with the evolution of Wi-Fi 7 and 8, all vital to optimize and monetize mobile AI traffic. And here you're providing the deterministic latencies, the localized high throughputs, and the consistency high connection rates to require delivered AI optimized connectivity slices for enterprises, edge AI applications, sovereign applications, which are guaranteeing performance, security, and very importantly, privacy as well. So what does that mean for testing? What is important to test? Let's start with the data center fabrics. So if you look on the left there, as I've talked about, as AI clusters scale out to these huge volumes of accelerators, testing the interconnect fabric, the 400 to 800 gig plus Ethernet is absolutely vital to keep GPUs fed rather than sitting idle, and to validate the throughput loss and their microburst behavior support. It's also critically important to test the collective communications libraries such as all-to-all or all-to-reduce, because they dominate the AI traffic and directly impact scaling and convergence times. Congestion control, validation under heavy and bursty loads is absolutely paramount to prevent buffer overrun and unfairness. And measuring things like job completion time and tail latency, they reveal the real business impacts, since overall progress in the training is gated by the slowest GPU worker in that sync cycle. And finally, don't forget to test encryption. Encryption performance is essential as east-west traffic is increasingly being secured, ensuring, and you need to make sure that those cryptography overheads do not erode the effective bandwidth or extend the training and inferencing times. As for the wireline networks, well, it's all about validating capacity on the core and peering links to ensure that the large model updates and the dataset transfers don't saturate the same backbone paths where other services are being transferred, your traditional services. Throughput on aggregation nodes needs to be tested to avoid hidden choke points that starve out edge AI clusters. Automated failover testing is a must to be able to test, to measure that, so that link or node failures do not degrade or stall jobs. And obviously it's critical to test out the new hard and soft slicing mechanisms so that you can guarantee predictable bandwidth and isolation for AI traffic. As for the wireline networks and the edge networks, well, there's a number of areas which are critical to test. You're talking about testing the connections per second to ensure that rapid session setups are supported, that application latency is delivered, that throughput, cache hit ratios, burst handling can be supported. Similarly, as on the wireline networks, encrypted latency overheads must be validated to make sure they don't impact or degrade experiences. But also uplink throughput and consistency is absolutely critical for multimodal data feeding the AI models. And of course, validating things like the 5G network slice performance and quality of service to make sure that the AI workloads are guaranteed alongside other services. So there's a huge array of areas that need to be tested if you're going to deliver these types of services. So how are you going to do this? So you've got a bit of a tester or a taster of what needs to be tested. I think the question moves on now to how. Now, leading customers we work with today are focusing first of all on three key methodologies. Let me just run through these quite quickly. The first is digital twins. Digital twins provide the emulated and realistic replicas of the networks and the AI workloads and traffic for risk-free repeatable testing. In essence, the emulators can replicate at scale complex AI traffic patterns, leveraging synthetic privacy-compliant data. And this allows you to validate the performance, interoperability, compliance, security, etc., under real-world peak loads and under those worst-case conditions. The second methodology is based on automation, intelligent automation, and that's powering two major test methodologies, continuous and active testing. Here, continuous testing allows test iterations to be spun up automatically. This allows you to run huge volumes of testing to get defects and degradations that would maybe only surface weeks in a live or a production environment or caught within the lab within minutes. And then on top of that, active testing across the live networks then predictively or proactively validates the real performance and user experience while providing you those feedback loops, which are so important for root cause analysis and relearning and reinforcement of the models. And the third methodology, of course, is AI test assistance. Just as AI is integrating or being delivered across our networks, testing is also using AI to support testing the intricacies and the dynamic natures. You saw the volume of test scenarios and iterations in the last slide that need to be covered. And AI assistance here can help automate that extensive testing, providing things like QAs, recommended remediations, and the test case development and execution itself. So what does that mean in the real world? So let's look at some of the actual solutions that have been executing these methodologies with our customers and leading data centers and network providers. Just starting, I'll just pick a few here from the list, but if you look on the left, the data center and testing the data center AI networking fabric. Now, to address the challenges here of testing and benchmarking AI clusters with realistic workloads, what the industry is doing is it's adopting the use of GPU workload emulation and clusterless testing, such as things like Keysight's data center builder, powered by automated test methodologies, which focus on qualifying AI networking fabric efficiencies. You're testing things like the Rocky V2 performance over those high-capacity Ethernet links, the performance of the various collective communication libraries, which are essential to orchestrate high-speed parallel data movement between the numerous GPUs. You're also able to test load balancing, especially to deal with large data transfers known as elephant flows. Congestion control, which is critical in preventing unnecessary slowdowns or packet loss impacting training efficiency and accuracy, can be tested, as well as monitoring and testing job completion times and tail latency to ensure synchronization among GPUs is guaranteed, preventing things like cascading delays. As for the wireline Ethernet networks, which primarily provide the interconnecting fabric in our telecom and enterprise networks, here, layer 2 to 7 traffic protocol and security emulators, such as Keysight's RS1, high-density Ethernet testers, and the SciPerf security and application traffic generators are being used to validate the high speeds, to test the implementation and performance of those routing protocols, segment routing soft slices, flex Ethernet hard slices, quality of service, and to verify security efficacy and performance impacts against new AI attack vectors, such as prompt injection attacks. And of course, if we look at the 5G edge networks, here automated 5G network and traffic emulators, including Spirent, Keysight's core network emulators, our UE emulators, application traffic emulators, and field test systems are performing a wide range of complex integrated testing. Here, they're used to validate the end-to-end 5G network slice performance, routing session management. You're there to use to test uplink performance and consistency, edge performance, including UPF distribution, and security across breakout, federated, and roaming scenarios. And of course, finally, you're also moving into the live operational networks with active testing combined with visibility fabric, such as packet brokers, to help you proactively test to monitor the visibility, the fault isolation, and the root cause analysis across transport and backhaul links, across the 5G over-the-air networks, and of course, edge offload, providing the enhanced localized performance, especially deterministic latency. Now, this comprehensive solution portfolio, which I'm showing you, It uniquely covers the development through deployment lifecycle, helping our customers to confidently design, build, deploy, and also operate networks for AI across data centers, wireline networks, and wireless infrastructure. And I'm very proud that we're pioneers in helping the industry not only embrace AI, but innovate and monetize it. And with that, I will hand you back to Solania if we have any time for questions. And again, apologize for the slight technical issue we had at the start.
Thank you, Stephen, for sharing your thoughts. It's perfectly fine. We're back on track. We have a few minutes left for Q&A, so let's jump right in. You highlighted the use of GPU workload emulation and cluster-free testing. Can you explain its significance compared to how testing has been done up until now?
Absolutely. I think this is becoming revolutionary, Solania, because up until this point, the only way to test the build out of these huge mega GPU clusters has been to actually use real GPUs. And that's obviously incredibly costly to have a replicated environment of very expensive GPUs. It's very difficult to make that repeatable. And having a methodology where you can actually emulate those GPUs, you can emulate the traffic and the workload patterns, and in essence create an environment which looks to the device or the GPU or the cluster under test or GPU under test as a huge cluster itself, is incredibly not only cost efficient, but gives you all the flexibility so you can have highly repeatable and realistic testing. And we're seeing a lot of the major players in the industry today now moving to this emulated GPU workload testing and what we would call clusterless testing. So it's really all about economies of cost and scale.
Can you talk a little bit about why security testing is paramount in the context of AI?
Yeah, I mean, there's multiple dimensions you could answer this, but I think there's two very important ones. One's about performance impact. As I said, a lot of traffic and a lot of the paths that traffic has to take, whether it's in the data center or whether it's in our wireline or wireless infrastructure, has to go through various security proxies, gateways, policy enforcement functions. And all of those can potentially have an impact on the performance of either the training or the inference response times. And it's absolutely critical to be able to test and understand those performance impacts so that you can either optimize some of the routing that you're doing, and you can optimize the types of security and layers of security you're putting in place. The other side of it, obviously, is the risk factor. Obviously, a key factor here is that not only in the initial training, but also in the retraining and continuous training that goes on, it's making sure that erroneous traffic or things like prompt injections aren't actually going to cause any impact and they're being caught. So being able to test that your systems and your security in place is able to actually deal with and is providing the relevant efficacy is highly critical as well. And that's why our solutions support those types of test scenarios in addition to validating the performance.
Right. Technically, the need for testing to optimize and tune the network for AI traffic makes complete sense. Well, what is the use case, business use case, or the ROI? What are the payoffs for businesses?
Yeah, I mean, the business case is really threefold. One's time to market. As I mentioned, these are very complex networks where you're either designing in the data center complete new architectures. In the wireline infrastructure, you're leveraging different technologies and protocols simultaneously, similar in the wireless networks. So being able to actually confidently and quickly validate that those network infrastructures are able to support your build out of that infrastructure so you can monetize it is absolutely critical. So time to market's number one. The second one is cost reduction. As I mentioned to you when you asked that the first question, which was asked around the testing, because up until this point the only way to test is to use real GPU, a huge cluster that you had to build out yourself as a test system or a bookend test system. The costs were phenomenal. So being able to reduce the cost down through a mixture of emulation and also automation actually is absolutely paramount. And the third one's energy efficiency. Again, coupled to all of this, Again, not requiring those huge cluster overheads, and being able to actually automate and do in parallel the combinations and iterations of testing that are required across those very, very complex networks and routing functions means that you're reducing the actual overheads in your lab environments and on the GPUs under test, again, reducing sort of the energy footprint that's needed through this process. So it's really those three key things: time to market, cost savings, and energy efficiency.
Mm-hmm. Excellent. Thank you, Steve, for joining us, and thank you, everyone, for watching the AI Infrastructure Week. The next session will start shortly. Stay tuned.
Thanks, everyone.